Good afternoon from Japan. So now we would like to start the keynote number 3. My name is Tateyama, chair of the local organizing committee. So it's a pleasure for me to introduce the speaker of the keynote lecture number 3. Before the keynote, let me explain briefly about the points of today's keynote. So in the 1980s in Japan, economy grew rapidly and we were facing to a serious labor shortage. So in order to cope with this situation, many companies have actively conducted the research and the development to introduce the robot technology to the real construction sites. However, in the 1990s, as economic conditions rapidly declined and the problem of labor shortage disappeared no longer, and the development of construction robots rapidly lost its momentum. Even under such situation, the Japanese government wanted to develop the construction robot for the future, but it was not allowed to introduce them in ordinary public works because the robot construction are more expensive than ordinary construction method. So Japanese government has taken a strategy to introduce the construction robot into the construction site, which were inaccessible due to the dangerous situation after natural disasters or confined narrow spaces for the maintenance of the infrastructure such as the drain pipe or so on. However, recently, research and the development of construction robots has become more and more heated again in Japan because the rapid decrease in the working age population has come to be recognized as a very serious problem for Japanese society. So development of construction robot has followed such a history in Japan. Today, I would like to invite Dr. Yasushi Nitta, representing the Ministry of Land, Infrastructure, Transport, and Tourism. It's an official name, so it's a long name, but briefly speaking, it's the Ministry of Construction. So this ministry has led the research and the development of construction robots continuously in such a social conditions. He will give a lecture on Japanese construction robot in public works today. After his keynote, we are going to have a question and answer time. If you have any questions or comment, please let us know in the chat board. I will select some of them and ask it to him, but time is so limited, therefore brief question and the short comment are easily to ask him, so your cooperation is much appreciated. So Dr. Nitta, please start your lecture today.
山先生、ありがとうございます。Thank you for introducing me. はじめまして。My name is Yasushi Nitta from Japanese Ministry of Infrastructure, Transport, and Tourism. Thank you for giving me the opportunity to introduce the Japanese policies, technology policies. At the ministry, I'm in charge of planning of promoting policies related to development and introduction robots used to infrastructure construction and maintenance and for disaster response. The government of Japan set up the new robot strategy in 2015. With the last 5 years as a robot evolution, intensive execution period. Under the new robot strategy, MLRT set a goal to be achieved by 2020s and have promoted its introduction intensively. 3 goals to be achieved in the public works in 2020. Apply intelligent construction to 30% of MLIT's contracts. Apply inspection robots to 20% of important infrastructures inspection. Improve the efficiency of unmanned construction to the same level as manned. We believe that these goals have been almost achieved. For example, ICT construction has been applied to 80% of the earthwork carried out by MLRT last year. In the new robot strategy, disaster response, inspection of infrastructures, construction are set as 3 priority areas. Regarding disaster response, there are high expectations for the application of robots to activities under conditions where people are exposed to the threat of danger, such as earthquakes, volcanoes, floods, and landslides. The photo, the upper left is UAV for high precision surveying the disaster area. The photo on the lower left, unmanned construction technology that stabilizes the collapsed mountain body by remote control from distance of 1 kilometer. Unmanned construction has already been put into practical use. It is realized by machine control based on video communication technology and 3D blueprint. In addition, the introduction of robots in disaster fields, such as floods and volcanoes, in one of our priority areas. As concrete goals to achieve this, for inspection robots, we will utilize robots for 20% of important infrastructure inspections. And for disaster response robots, we have set the target to realize construction efficiency, which is not inferior compared to manned construction. This figure shows the overall pictures of the field verification project. We recruited inspection robots for 3 years and verified their function on the actual site. For bridge inspection and tunnel inspection, we plan to certify performance of the robot for the requirement. In addition, we like to propose a new inspection method using robots, achieve more efficient maintenance management. On site verification, various types of inspection robots were proposed, exceeding 100 technologies. The background to MLIT's strong promotion of the introduction of robots into the public works project is the existence of issues such as Japan being a disaster-prone country and labor shortage due to the aging of society. Furthermore, in order to overcome the labor shortage in the construction industry, there is an urgent need to improve the productivity and safety of construction work. In particular, Japan is one of the most earthquake-prone countries in the world. There are 4 large plates around the Japanese archipelago. Many plate-type earthquakes occur, and volcanic activity is active. Following the Great East Japan earthquake in 2011, the magnitude 7.3 earthquake hit Kumamoto in 2016, causing devastating damage. In Japan, we have to strengthen our national land and make effort to countermeasures for large-scale earthquakes, such as capital inland earthquake that has a strong possibility to Japan. The introduction of full-fledged unmanned construction technologies began with restoration project after the volcanic eruption of Mount Unzen-Fugen in Kyushu in 1991 first. As shown in this photo, the pyroclastic flows and debris flows caused by the volcanic eruption hit the town. Serious damage occurred, and schools were burned down by the pyroclastic flows, and houses were buried by the debris flows. The eruption left 44 people dead or missing and damaged 2,511 buildings. During the eruption disaster, the removal of sediment that becomes a source of debris flows was urgently needed in danger zone that might be reached by the pyroclastic flows with a speed of 100 km/h over. For stone removal and erosion control works such as dosing, soil gathering, excavating, loading, and transportation, a technology was developed that implements construction by remote controlling heavy machine equipment with GPS using wireless communication. Initially, construction work was carried out in conditions of temperature at 100 degrees Celsius and 100% humidity, and during the construction work, rock size of about 2 to 3 meters had to be crushed and removed together, with earth and sand by remote control from more than 100 meters away. Thanks to decision to adopt technologies, we could achieve the excavation of channels, the construction of concrete debris or debris barrier, and installation of steel slits, all without human entering the construction site. Not only could we reduce the risk debris flows and pyroclastic flows, but construction companies and equipment manufacturers could also gather experience and know-how, and unmanned construction technology have progressed greatly. At first, we started with radio control bulldozers, but now it has become possible to work from control rooms, which are more than 30 kilometers away from the construction site. This slide shows remote control of underwater bulldozer, which began around 1969. And unmanned construction makes full use of information construction of recent years. We call ICT construction. Bulldozers and excavator works together, and work capacity has improved dramatically. Now, I want to give you a short introduction about UCS, Unmanned Construction System, with the most simple direct operation method. And the operator conducts a remote control at a close range by direct visual observation. Operation distance is limited to a range of about 50 meters, at which visual observation is possible. This we call the first generation. The second generation is a method by using a camera image, generally for a range of less than 300 meters. If you use a radio relay vehicle, you can conduct remote control up to the range of about 600 meters. Roller compacted concrete method, a leveling and compacting method using rollers was introduced to build concrete dams with molds using gravel. In the Haksan erosion control project, debris barrier construction work was conducted using a 50-ton suspension crane. All the construction work, such as earthwork, the setting up of the cylindrical mold block, concrete pressing, compaction, and construction joint processing were conducted by remote control. Unmanned construction with the ISM method, in situ mixing method, which utilizes the gravel available on the construction site, was also conducted. With the third generation, we improve work efficiency by introducing machine guidance and the machine control using design data. UCS have evolved through actual disaster response since the volcanic eruption of Mount Usu in 2000. Their application in urban areas has been required, and remote construction from a long distance of more than 1 kilometer has become possible. Since 2000, reconstruction work with greater accuracy has been realized thanks to progress of surveying technology, such as GPS, the pitting of concrete block, the construction of debris barriers using cylindrical molds. In addition, since 2005, with the introduction of informatization construction, machine control has been used, and the efficiency of high precision construction has made further progress. With a fourth generation, by compressing and exchanging high volumes of high-definition image data through a communication network, remote control from ultra-long distance, more than 30 kilometers, has become possible. Network type UCS was put to practical use through on-site validation at Mount Unzen in 2011. The installation of operation was carried out quickly in just 1 hour. During this experiment, in addition to optical cable communication over the distance of 80 kilometers, a variety of communication methods such as satellite, mobile phone, TV radio waves, and long-range wireless LAN were applied. Fourth generation UCS is said to be the further construction technology that utilizes information network and ICT. This picture shows UCS was introduced for work to remove the unstable debris at the top of part of deep-seated landslide that had occurred in Nara Prefecture. This is an aerial photograph of the disaster site in 2012. The operator performed the operation at a distance of about 1 kilometer from the heavy machinery. From the operating room to the place near the site, optical fiber has been laid, and video and machine control data is communicated via wireless LAN. By creating three-dimensional construction data, which combine design information with topographical information obtained in advance by aerial survey, safe and high-precision construction become possible. In particular, as a blade is operating automatically, it has become possible for the operator to level to the design height by performing only forward and reverse operation. This is work performed by machine control type bulldozer. The blade is automatically controlled. The operator can concentrate on performing the reverse and forward. In addition to the small camera image, he is looking at, there is a small display. There, the excavation section, that is a work target, is displayed based on the three-dimensional design data. There's an excavation section that is work target displayed based on the three-dimensional design data. The number of the lights show the difference between the design value and the blade height. Below that, designed gradient of the ground and the angle of the bulldozer blade are displayed. In this construction, all machines are done by remote control. Also, remote control is not autonomous operations. It should be noted that this is a dangerous area where a landslide may occur again due to aftershocks and that manned construction cannot be performed. Our originality is to propose an effective new technology that can be used at the actual construction site to carry out construction in order to prevent the spread of damage in dangerous area where people cannot enter. And the construction was able to be completed by combining the technologies that can actually be applied. A specific example, we will introduce the realization of saving labor and becoming automatic control of crawler carrier and remote control excavator. Uh, 55 people were killed and more than 180,000 people were evacuated from the Kumamoto earthquake. And about 8,300 houses were completely destroyed and 160,000 houses were damaged. The Aso Bridge collapsed due to the large-scale landslide caused by the earthquake. This video shows the situation in the Minami Aso area taken with a drone. There are arch bridge in front of the building that are let through, but it collapsed. This image, you can see the wooden structure miraculously enduring on the stone wall of Kumamoto. This image is a Kumamoto castle. You can see the right hand. There is a stone wall. This is a miracle. But it's very dangerous situation. A remote control unit called Surrogate, introduced by Obayashi Corporation, is used for this restoration work. To restore the stone wall, which is cultural property, it is necessary to collect each stone, walking directly under ishigaki, where there is a risk of collapse due to aftershocks. It's extremely dangerous. Surrogate system can be operated remotely by attaching a camera and a control device to an ordinary hydraulic excavator. Unexpected heavy rains and floods are also on the rise due to the progress of global warming. This video shows damage caused by the overflowing river that was damaged by the collapse of the mountain body that occurred in Kyushu in 2017. UAVs are now investigating dangerous locations. If the valley collapsed, the natural dam will be performed. Natural dam will be formed. More dangerous situation will occur. This slide shows a river blockage which occurred in the areas affected by 2S earthquake of magnitude 7.4 that occurred in October 2004. In this village, landslide caused a 52 river blockage and the formation of landslide dams. In this area, the great volume of damming sediment, pumping drainage with emergency drainage channels was carried out in a 24 hours operation in order to prevent a collapse of the dam by overflow. This slide shows the natural dam almost overflow with a height of 31 meters. At this time, several landslide dams also occurred in this downstream area. Because a water channel to prevent a collapse by the overflow had to set quickly, UCS with its low efficiency was not applied, and water channel excavation was carried out with manned work under dangerous conditions. Workers were working while being exposed to the danger of being hit by mudslide from upstream. This picture shows the dam from the previous slide, seen from downstream side. Landslide sediment has been scoring by drainage. In order to prevent collapse by scoring, the helicopter has dropped the concrete block and ready mixed concrete. This was quite a dangerous situation. This is a situation downstream. Due to the landslide dam, a vast dam lake has occurred. Here you can see the roof of submerged houses floating on the water. Quick response is required before the situation becomes like this. What is the value of robot realize in public works? It is to realize the safety of people's lives and the economy. In this case of the natural dam mentioned earlier, if the UCS started quickly and the work efficiency was high, it may have been more effective in preventing the spread of damage. The technology some evolved. However, further evolution is still required. Improving work efficiency is important. In Japan, in order to foster the technology, we have adopted this technology to activity, disaster restoration work. So far, UCS has been adopted at more than 150 sites. It has given good results at landslide disaster sites all over Japan. We MLRT deploy a remote control type excavator in each regional bureau. In addition, these excavators can be disassembled so that air transport by helicopter become possible. The photo on the right-hand side shows a RoboQ, called RoboQ, a device to enable the remote operation of a general purpose excavator by loading on the driver's seat. PWRI is a national institute in the field of civil engineering. Is developing ROS platform for ICT construction in order to promote further technological development of robots and software. We have already prototyped remote controlled excavator and simulator support that support ROS. This year, PWRI will set up next generation unmanned construction test fleet using a 5G network in Tsukuba, Japan. We aim to contribute to reach development by various developers utilizing common rules. With regard to disaster recovery, the construction industry has played an important part. However, in Japan, we are facing full-grown aging society, and the number of skilled workers has been especially declining rapidly. This shocking graph shows the fact 35% of skilled workers are more than 55 years old, and there are only 10% of workers who are less than 30 years old. A labor shortage is expected due to mass retirement in the next 10 years. Therefore, because of the need to enhance the productivity of the construction industry. And now I mentioned to deal with aging of social infrastructure in Japan. Their total number of bridges is about 700,000 as of 2010. Those 15 meters or longer that were more than 50 years old accounted for 8% total. That percentage is expected to raise 53% in 2030. This picture shows accident that tunnel named Sasago Tunnel, which roof slab collapsed over the 130 meters in the expressway, and 9 persons were dead. Failure to implement hammering test during periodic inspections was found to be the reason for the accident. With this as a turning point, emergency inspections have been conducted to tunnels all over the country, and lots of problems were identified. This strengthens our conviction that consistent repair and improvement efforts are needed if social infrastructure is to be used over a long period of time. This photo shows a diagonal member of steel truss bridge broken due to the collision. This bridge is Kisogawa Bridge, constructed 50 years ago. Identification of problem through inspection and countermeasures for the defect found, such as crack in wheels, are becoming increasingly important. Our road law was revised in 2013 to make it mandatory perform close-range visual inspection of tunnels and bridge every 5 years. Eshima-Ohashi is Japan's largest concrete bridge with total length of 1.7 kilometers and a height of 44 meters. It will be the third largest PC rigid frame structures bridge in the world. Since the slope of this bridge reaches 6%, it's difficult to frame bridge. It is very difficult to regulate alternate traffic, and the use of robot has been desired. At SIP, a strategic innovative creation program, developed the bridge inspection robot, evaluated the ability to detect damage such as surface crack. In this area, wind speed can reach up to 10 meter per second. So inspection of rich girders required ability. Compare the size of the robot and the bridge. Image how large civil engineering structure is and how huge amount of image data needed to be managed to detect cracks with a width of a small 0.2 millimeters. So this robot developed the program of SIP. We are promoting not only verification, but also promoting technical development as cross-ministerial project. We call SIP Strategic Innovation Promotion Program for a 5 years project. We intended to carry out the development of new technologies that will be needed in the near future. We will develop environment favorite for introduction of robot technologies. For example, we are studying the structures most appropriate for robot inspections, and the research and development work is being done on the robot information markers. Introducing the underwater heavy dump truck jointly developed by the government and private companies. This vehicle is a dump truck that weighs 10 tons and can run to the depth of 2 meters. In flooded Japan, this vehicle is useful for quick recovery work in flooded areas where ships with depths below 2 meters cannot be used. It is a remote controllable carry equipped with a non-contact underwater sensor that checks the underwater terrain to realize safe driving. This video demonstrates that in the riverbed excavation work of Kyushu is Kuma River. The river with a maximum depth of 1.8 meter was crossed 100 meter speed of 8 km per hour. It was confirmed that there was no problem with flow velocity of the river up to about 5 kilometers. In the growth strategy, which is a budget guideline set by the Japanese government, the Ministry of Land Infrastructure, Transport and Tourism strongly emphasize productivity improvement in the infrastructure field. Increase construction site productivity by 25% by 2025. To that end, we will introduce core technologies such as AI and robots to popularize ICT construction. We will also utilize BIM in the public works project by 2023. The government has declared these goals. So in order to quickly and carry out the recovery work efficiency in this project, and we implemented functional verification at the actual site. In addition to the 2 areas of damage surveys and emergency recovery, we designed the 3 areas of maintenance. As a result of on-site verification, we have been promoting the use of those technologies that obtains excellent evaluation. For on-site verification, we anticipate the collapse of tunnel, volcanic eruption, landslides, and debris flows. And disasters for which robots are expected to be utilized. As for the type of robot, we anticipate the use of flying type, crawler type, drainage robot, construction robot. A total of 100 technologies were checked in on-site verification as providers responded to the public recruitment over a 2 years period. Disaster survey robot includes UAVs with laser scanner. The UAVs are capable of sampling volcanic ash. There are also robots with penetration tests, which are capable of surveying the bearing power of ground, and robots capable of surveying collapsed tunnel. Among the emergency response robots are the autonomously controlled vibration roller and mounted robot used for remote control of ordinary construction machinery. This photo shows actual collapse of 20 tons of the concrete during the earthquake. In this project, unmanned survey robot performed a survey while transmitting live on-the-spot image over the length of the dark tunnel, 700 meters long. First year, but all of the applicants failed. But second year, the technology was completed the investigation of 700 meters. This flying robot can achieve the rapid survey of the inaccessible location. Here we will introduce some technology that receive high evaluations from the view of accuracy, transportability. This slide shows a step for full-scale introduction. In addition, 2 areas, damage surveys, emergency recovery from disaster, we designated 3 areas of maintenance. As a result of on-site verification, we have been promoting domestic use of the technologies that obtained excellent evaluation. Some example by including disaster agreement. In order to develop the deployment of inspection robot, it planned to develop for the inspection and inspection procedures that can demonstrate the features of the robot, how to use the robot in the inspection, outcome, how to organize the delivery method, data that the robot acquires. So now I'd like to mention about the aiming of trial introduction of robot. The use of inspection robot in social infrastructure maintenance offers merits of labor saving and keeping reproductive record. For trial introduction, we'd like to propose not only robot operation procedures, but also method used to deliver the inspection record. Data acquired by robot is most valuable for infrastructure administrators. Current inspection method depends on manpower. Only the enlarged photos of detected damage are left available. As an infrastructure DX, digital transformation, MLIT is promoting the introduction of BIM, SIM in order to improve the efficiency of design, construction, and maintenance cycles. In particular, we are working on the method to manage a large number of inspection images using 3D model. This is an example of 3D viewer of inspection image. It is 3D model that automatically generated from SFM from 1,000 photos taken by UAV. The position and direction in which the picture was taken are expressed by a pyramid. Inspection pictures of large structures requires a lot of time and cost to organize the location of the damage. This technology is capable of automating work. In the near future, photo management with 3D model will be expected. MLIT have started develop robot inspection business system by using AI with private companies. Inspection robots, unlike people, get large number of photos and videos. AI can process faster than people to decipher large amounts of image from robot. In order to improve the efficiency for robot inspection, we aim to achieve high detection efficiency by AI. Additionally, we will develop supervised data with the input of expert, and we will promote the installation of evaluation system. We'd like to propose to the local government of Japan that manage the huge bridges and tunnels records and store inspection image in 3D model. However, I think that in order to do so, need a viewer that conforms to the form of the inspection report, the standardized inspection guidelines. In addition, local governments and administrators in Japan think that's desirable to have data in Japan because they are concerned that the data will be lost due to some kind of trouble. I think that the operation form of putting the cloud server, which accumulates data in Japan, and putting the program in the United States is good. I think that it is possible to propose an effective business model by preparing a viewer corresponding to inspection business standard and downloaded function of the generated data. We hope that ISARC will lead to energetic technology exchanges and the realization of excellent rewarding business activity. Thank you very much. My speech is over. Thank you very much.
Okay, thank you so much. So I think that you have a lot of the topics that you would like to introduce, but we are sorry, but we cannot prepare enough time for your lecture. So I have a lot of the questions. So Dr. Nitta, do you see the chat board?
Yes.
The chat board, okay.
Just a moment.
So please check the chat board. So first question, do you see the Dr. Boroja Garesha de Soto? Do you see the long question?
Boroja-san.
Yes, Boroja-san. Because he must move to the next session because he is the session chair of the next session. So I want to pick up this question. So many of the remote operations you indicate heavily. I think the problem of some of the hacking between the machine and the operators. Do you understand?
Yes, just a moment.
Yes.
Some cyber attack, you mean?
Yeah.
Yes. Yes, it's very important. Now we are just planning to prevent the cyber physical attack. But so Japanese government has decided to began to start a cloud system to manage the data related to infrastructure, but not have started yet. So this year we will constructing the database for digital transformation. So we will just starting to study.
It will be very important, but the serious, the subject that we must tackle from now. Yes. Okay. Thank you so much. Good point. I think so. So, would you see the chatbot again? So the first question is about the radiations. Radiation, the first question. So from the Dr. Wilson Chow, radiation, 放射線です。福島とか放射線で影響がないかということだと思います。
それって福島の話ですね。
福島の話。放射線で機械が影響を受けなかったかという話です。
I don't know detail about the activity of the Fukushima nuclear plant recovery work, but some of how do you say influence to the electronic devices, as you know, but other places we have no trouble. Like I don't know, this kind of trouble has reported.
Yes. So I've heard that we worry about the effect of the radiation in the recovery job from the nuclear plants. Yeah, we worry about it, but I've heard that not so big the effort the construction robot has been, they got not so big the effect we don't see in the unmanned controlled system from the radiation. I think so. Is okay, Nitta-san? So the
so yes, yes.
Okay, so next question. Okay. So next one is thank you for the fascinating presentation. How many cameras were placed per equipment? 360-degree view may be required for working in the dangerous construction?
Yes, some work sites have already applied such a 360 round view cameras. Some work sites have applied the integrated image data, how do you say, round view monitor, and most of the work sites applied UCS, so they applied 2 or 3 cameras for each machinery.
2 or 3
it
cameras.
Depends on the size.
Okay, so I want to discuss about the time is limited. So now we have come to the end of our allocated time. I would like to close the keynote number 3. So when we started the preparation of the symposium last year, we are willing to show some of the real construction robots that Dr. Nitta introduced in his presentation. So however, we can't show you the real machines at the online symposium. So we have prepared the video site to introduce some of the Japanese construction robots. So also, the videos on the site are just a small part of the Japanese construction robots, and half of the videos are explained in Japanese. But we hope you can see the current status of the Japanese construction robots. So please refer and visit to the website of the online symposium. We paste a lot of the number of the videos is I think the 20 videos we pasted. So please visit the website of this online symposium. So Dr. Nitta, I think that your lecture has given a deep understanding of the current state of the Japanese construction robot technologies. Thank you again for your interesting presentation.
Thank you very much, Tateyama Sensei.